So
Yes.
today we are very happy to have Mohamed Barakat from Universität Siegen to talk us about organizing computer algebra using category theory. So
Thank you very much for the invitation. I'm happy to be here. I'm seeing a couple of known faces that I'm also happy about. And Alban will be mentioned explicitly in this talk. So this talk is summarizing our ongoing activity of reorganizing computer algebra using category theory. Of course, the main motivation was to go up in the theory, to get more abstract stuff done. But as we are advancing, we see that we can actually go even further down and organize things like rings and graded rings using category theory. And once you go up, you don't have really many competitors. But when you go down, people start screaming that this will be devastatingly slow. And they are right in this critique. And what we are doing now, where probably I wouldn't have time to talk about it, is that we are developing a category theory compiler, so that the code that the resulting code can really be compiled in a usual sense, that you really can compile it down to assembler and get rid of all the categorical overhead. So let me start. So here is a list of seemingly unrelated problems. I'll try to come to most of them today only via worksheets or Julia notebooks that you will see on my laptop. You see here I have prepared some of them, so I will be switching back and forth between this, and you see I have already prepared some Julia notebooks, 1, 2, 3, 4, 5, 6, 7, 8, 9 even. So let's start with some seemingly unrelated problems. So given a system sigma of polynomial equations and inequations, this is what I mean by inequations, so not equal to, with parametric coefficients, then the question is for which parameters is sigma solvable over some field, or with integral coefficients, and then the question is for which characteristics P is sigma solvable over a field or characteristic P. So I'll come to this question on, well, probably on the very last notebook. So how can we model coherent sheaves and compute sheaf cohomology on the computer? Is there an equidimensional decomposition of systems for systems of linear differential equations? How can we compute spectral sequences and modules of modules and sheaves on the computer? And can we prove the snake lemma on the computer? And actually, there are more questions that somehow are in reach of our categorical approach. So this is how we think about computer algebra through a unified categorical approach. So computer algebra can, in principle, solve all these problems and much more. However, the classical approach leads to mathematical approaches which may look very different. And the resulting code might be humongous and or unintelligible. So you can look at the code and you don't really understand much. And category theory is, among other things, it's much more than this, but it's also an excellent organizational language for algebra. And you read in my abstract that I view algebra as the mathematics of mathematics. So maybe category theory is then the mathematics of algebra. So it's the mathematics of the mathematics of the mathematics. And even more so for computer algebra. And this is actually what we discovered, that there are fields of mathematics where we don't need to debate with people about the value of category theory. And of course, in other fields, even in algebra, we need to. But since we're working in computer algebra, we ourselves discovered the immense value of category theory. And it is in some sense even a higher level programming language for algebra, and I would like to convince you of this throughout the talk. So first of all, what do we expect from a programming language? Any questions so far? So what do we expect from a programming language? So we expect some types at least to start with. And we expect some constructors of data structures of the available types in the system. And we expect some algorithms acting on the data structures. And we expect, in a good programming language, well-documented, very clear specifications for the algorithms. What is the specification of the input? What is the specification of the output? Expressivity, so the ability to reach complicated semantics using simple syntax. And I hope you will see this also throughout the talk. Compositionality, this is now the name of the journal of the applied category theory community. So this should be somehow a bit more general than just composability. So compositionality means composability everywhere. Yeah. So the ability to build new types, data structures, algorithms, and specifications from existing ones. You want, of course, to enlarge your system. Okay. And I hope you see all of these 6 things in the talk. So I hope to be able to convince you that category theory naturally offers all of the above and much more. Okay, so let's start at the very beginning, even before categories. What is a quiver? Some people call this a multi-D-graph. Some people just call it a D-graph or digraph. I like to call it a quiver because I have connections to the community which study representations of quiver. I don't even mean finite quivers in general, but in the examples you'll see here, they'll always be finite. So this is part of the definition of the category, and it even plays another role that you will see after, I think, 3 or 4 slides. So you can think this as the first approximation of a category, and it already has much of the points that we discussed about, but actually almost no specification. So a quiver is a data structure, Q, with some symbols that we should understand now. It has Q1, Q0, S, and T, of type quiver, consisting of 2 parameterized types. So one denoted by Q0, now you know what Q0 is, and called objects of Q, and one denoted Q1 and called morphisms of Q. 2 constructors of data structures of type objects out of some data that we have. You'll see this data in a moment. And another constructor of the data structures of type morphism out of 2 objects and some data. 4 algorithms, so 1 to decide equality of objects, 1 to decide equality of morphisms. This is in our application optional. You should think of maybe infinite complexes. They also give you a category and in particular a quiver. And if you have a data structure having infinite complexes, then you really can just compare them locally, but you cannot compare them everywhere. But of course, it's nice to have. And what we put a lot of effort to put our hands on an algorithm to decide the equality of morphisms. This will come again towards the end of the talk. We have an algorithm called source, which given a morphism gives us its source, another called target. And in the worksheets that you will see, or the Julia notebook, you will see this target will be called range. This has to do with historical technical reasons in GAP. I wanted it to be called target, but at that moment when I started my project, target was hijacked in GAP. Now it's free again. So Here is an example of a quiver. So it's actually, as I just mentioned, it's just a directed graph that can also have loops and can also have multiple arrows. I just drew one arrow between every object. So here is already our first worksheet. So I'm loading a package called cap and homalg. Homalg is a project that I started when I was collaborating with Alban many, many years ago. It stands for homological algebra, and you probably know Alban's Skype name. It's also called homological algebra. And at some moment, I figured out that homological algebra needs much more category theory than I imagined at the beginning. And I had two very excellent PhD students, Sebastian Pozo and Sebastian Gutsche, and I asked them to enhance homalg with categories, but they ended up writing their own project. It's called Categories, Algorithms, and Programming. This is the same acronym as for GAP. GAP is coming from Groups, Algorithms, and Programming. And you know, a category is a generalization of a group, as you may know. So this is here a Julia package, which is just wrapping many GAP packages that we're using. And homalg also has the ability of invoking other computer algebra systems in the background, like Singular, Magma, or Sage, and so on, so that we don't need to reinvent wheels all the time. And among the packages that belong to this homalg cap sphere, there is a package called algebroids. We just need part of it now and more of it later. So now I'll go and now define the quiver. You see now I have to tell it that you are a quiver with two objects m and n. Phi goes from m to n, alpha goes from m to n, and psi goes from n to n. So you see this is exactly what I have here at the bottom. So let's activate this. My computer is slow, I think because of the BBB connection. So now you can, from the quiver, get the object m, the object n, you can get the morphism phi, and because we are in Jupyter, we can even use the UTF phi and the UTF alpha and the UTF psi. Yeah. So we cannot actually do much more because we just have things like source and target, but there is no real specification. Maybe one specification is that that the source of alpha, as we had it here, should be m. Yeah, and this is something we can compute, and it looks like m, and we can ask, is it m? And true. So this is the range that should be called target, and here is alpha and its range, and the range is indeed n. Okay. I very much dislike about Julia that they're using the equal for the equal. So this is really something I hate about Julia. Okay, so let's go back to the talk. And now we continue our journey to what is a category. So up to now, you didn't really see specification, and you didn't see expressivity, and you didn't see compositionality. So a category is a data structure, not just Q0 and Q1, but you have now C0, C1, C2, and actually this can go indefinitely if you want. This is then called the nerve of the category. So this is a data structure of the type category of subtype quiver. So maybe it's the other way around, subtype category of type quiver. So it's a subtype of category. This is what it meant, with two more algorithms which use the constructors. One is called the identity morphism one, which you see in the diagram above. And one is called the composition. It goes from this fiber product over the morphism class with itself over the object class. So these are the composable arrows, this C2, satisfying certain specifications or axioms. We call it axioms in mathematics. Computer scientists would say specifications. So here is two of them, but you can think about the rest. Maybe that the source of 1m means one of m, where m is an object. The source of this is m, and it's also the target. and the source of the composition of alpha and phi is the source of alpha. And you can complete the list on your own. And of course, you need associativity of the multiplication and so on and so forth. So our first category constructor is the constructor of the opposite category. So you can start with a category having a lot of algorithm, not just the 6 that you now know. So the decision of objects, decision of equality, the source, the target, the identity, the composition, but depending on what the category has as properties and so on, it can have much more, and we will come to this in a moment. And what you can do is you can now take the opposite construction by just looking at every arrow and say it just goes into the opposite direction. And we also have this implemented on the computer. So category theory actually offers more types and specifications. So a type called 2 category, etc. So you can go indefinitely 3 category and so on. And then at some moment it becomes fuzzy. And then it becomes well-behaved again when you reach infinity categories. At least there are some models for this. So the category cat of categories as a data structures of type 2 category consisting of categories as objects, also known as zeromorphisms, functors as one morphisms between categories, natural transformation as 2 morphisms between functors. And by this, we get more specification for morphisms. So we speak about AP, mono, split AP, split mono, split iso. ISO or isomorphism. This is the same as mono and split AP or AP and split mono. You can have more specification for functors like full, faithful, existence of weak limits or co-limits of functors. You can get more specification for objects, an object being initial or terminal, or initial and terminal, called zero object, projective, injective. All these are categorical properties. And you also get more specification for categories. Discrete category is a category which only have the identity morphisms, so only the one dictated by the specifications. Locally small categories where the class of morphism between 2 objects is a set and not a class, but for us on the computer, everything is just a set. Small means even the object class is a set, which is also the case when we do constructive category theory. Thin means that between 2 objects, there is at most one morphism. Skeletal means that isomorphism of objects means equality of objects. Groupoid means that every arrow is an isomorphism and has thus an inverse. Existence of certain types of co-limits of functors from certain categories. These categories are usually called index categories. And depending on the index categories, you talk about products. We will come to this later. Co-products, byproducts, direct sum. I'll also say what is a direct sum. But also equalizers, co-equalizers. And if we have 0 objects, we can talk about kernels and co-kernels, pullbacks, push-outs. And specification of categories are usually called doctrines in the modern literature. And here are some of them. And I'll also use some of them in the talk. So pre-additive, a generalization of this is called k-linear. So if you specify the commutative ring k to be the integers, you will recover pre-additive. You have then k-additive, pre-abelian, abelian, co-Cartesian, co-closed, topos, and so on. So it goes as far as you like. So here is a warning. You see on the previous slide, I'm just saying we have kernels. If your brain is wired from set theory, then you will think that a kernel is just a subset of the source, those elements that map to 0. And in category theory, this is much more complicated. So let phi be a morphism in the category C. The category C should have a 0 object. And once we have a 0 object, we can then say what is a zeromorphism. So what is a kernel categorically? A kernel categorically is not just one thing. It's actually 3 things at least. So it's an object called kernel phi. This is the first specification. Yeah, and the first part of the data structure of the kernel. The second thing is the existence of a morphism. This is also a specification, which goes from kernel phi to M, such that the composition of these two morphisms is 0. So now we have two constructions, kernel phi and kappa, but we are not done yet. We also want that for every competitor, for kappa, we have a lift, such that the leftmost triangle is commutative. If we insist on this lift to be unique, we then talk about the kernel. Otherwise, we talk about the weak kernel. Okay, and I will use also weak kernels in the talk. So as you see, when we say a category, we actually meet an entire computational context. So this is a data structure having a bunch of algorithms inside, every one of them very nicely specified. We have a specification online, but you actually can open any category theory book and see the specification of our programs. Yeah, we don't need to invent our own specifications. We're just faithful to the language of category theory. So what about the expressivity of category theory? So you remember expressivity was the ability to reach complicated semantics with simple syntax. So a foretaste before we come to the more interesting stuff. So on the left, you see classical structure. On the right, you see doctrine of small category. So a set is just nothing but a discrete category. We're just talking small categories now. A proset is nothing but a thin category. A poset is nothing but a skeletal poset. A setoid, this is a set with an equivalence relation. This is a thin groupoid. A meat lattice is a called Cartesian lattice. Yeah, I will come to the notion of Cartesian category later. A joint lattice is a co-Cartesian poset. A lattice is a Cartesian co-Cartesian poset. A Heyting algebra is a Cartesian closed lattice. A co-Heyting algebra is a co-Cartesian co-closed lattice. A Boolean algebra is an exercise. A monoid is a category on one object. A ring is a pre-additive category on one object. A K-algebra is a K-linear category on one object. So you see already the language. You look at the left-hand side and you see the many names. And on the right-hand side, you just see a category with specific doctrines. Yeah, but it's all a category. You can just need to teach your computer more or less just one data structure with many doctrines. Okay, so you see, this is the beginning of expressivity of category theory. We can express a lot with just a category and its many doctrines. But if you know enough of category theory, there is something very important still missing, and actually most important. Maybe you can guess it, it's the adjunction. So this is what is called the adjunction of functors. If you don't know it, then maybe this is not the right place to talk about it. I'm just telling you that this is one of the central notions of category theory. You should learn it if you're interested in this topic. And here is compositionality of category constructors. So the quivers together with functors, so we can also define functors for quivers, not just for categories. They themselves form a category called quivs. Cat is the two categories of categories, but we just look at it here as just one category. So just we look at the categories and the functors as morphisms. And on the rightmost side, we just look at the K-linear categories. And we see that we have a free category constructor that takes us from a quiver to a free category. We have a constructor that takes us from a category to a K-linear category. This is called the K-algebroid. And another abbreviation is this K brackets. This should remind you of the group algebra. And actually, this functor is generalizing the group algebra constructor. And on the back side, you have the forgetful functors. So you forget that you have a category and just remember that every category is a quiver, and you forget the K-linear structure. Just remember that every K-linear category is just a category. And you see from the existence of this right adjoints, and every adjoint is a unique, every left adjoint is a unique, and every right adjoint is a unique, you see that you just need to think about the forgetful functor and ask yourself, is there a right adjoint? Is there a left adjoint? And in this case, you get a universal answer. Yes, there is a universal construction called free category, which goes from quivs to cat. And another universal construction is called algebroid, which goes from cat to gcat, to kcat, I'm sorry. So, and whereas monoids are generated by sets, categories are generated by quivers. So let me now show you worksheets or notebooks demonstrating this. So now we are back to our notebooks, and now I go and define my quiver again. It's still the same quiver. And now I define the free category, and it's telling me the category freely generated by the right quiver. I can tell him, show me some information about this category. It tells me it has 13 algorithms, which were installed just using 7 algorithms. And these are all of them. So this is the identity. It is congruent is actually the mathematical equality of morphisms and so on. And the precompose is the composition. These were primitively installed, and we get these others here for free. For example, if something is 1 or... Okay. So what here we can actually do a bit more. So now we can, again, extract the generators of this category. We can now ask, are you an endomorphism? We can get alpha, ask for the source of alpha, the range of alpha, and psi. This is not much more than we can do for quivers. Actually, it's the same, but now we can compose. Yeah. So now we can compose phi and phi. Now we can compose phi and alpha. Now we can compose alpha and psi. Now we can compose alpha, phi, alpha, psi in this order. And if we try to compose alpha and phi, so this is really, you are composing in the reading direction. So first alpha and then phi. And here you should get an error. Okay. But if we now pass to the opposite category, then this will be in the opposite category. I just reverse the meaning of the arrows. So here I construct the opposite category. And now I take phi op to be the same morphism, but interpreted vice versa. And alpha, the same morphism. And now you see it's now going from n to m and not from m to n. And now I can precompose vice versa. Okay, so let's go to linear category. This gives me the first circle here. And now I want to look at the second circle. So this stuff is already preloaded. So, and now I take the commutative ring K to be the field of rationals. And now I do the algebroid. So this is exactly like the group algebra. It's the same construction, but actually can be applied to categories and not just groups. Groups are groupoids or one on one point. So this is telling me I'm the algebroid freely generated by the right quiver. And I see now there are 21 operations installed for this data structure called category, coming from 11 primitive algorithms. And here are the 11 primitive algorithms, and here are all the 21 operations that got installed. Okay. And what can we now do here? So again, I can extract the morphisms. But now I can add 2 morphisms, which didn't make sense for any category. And now I can precompose minus phi with alpha plus alpha. And because I also have the rationals, I can also multiply with 1/2 or 3/4 or something like this. Okay. So you see now I can do more. I get more algorithms in my data structure. So let's continue with our journey. So let's look at this doctrine of being Cartesian or co-Cartesian. So a finite product of objects M1 till ML in a category C is an object P together with morphisms pi1 till pi L. And exactly like with kernels, you have the relation with other competitors. So such that for any other competitor, P prime, also with morphisms phi1 till phi L competing with pi1 till pi L, there is a unique morphism from pi prime to P prime to P. And then you can say the empty product is called the terminal object. This was one of the previous slides. The category admitting finite products, including the terminal object, is called Cartesian. A coproduct of objects in C is a product in C op. So I don't need to define it. This means just go and switch all the arrows in the diagram and you get the dual definition. The empty coproduct is called the initial object. A category admitting finite products is called co-Cartesian. And now there is an instance in which these guys coincide, namely for so-called pre-additive categories. So, but in general, a byproduct of objects in C is a product and a coproduct simultaneously. This might not exist in general, but they do exist in pre-additive categories. Every product is automatically a coproduct. And one can slightly modify the arrows such that we get a stronger compatibility between the product and the coproduct, and then we call them direct sums. And we denote them in this classical way. So a pre-additive or k-linear category is called additive or k-additive if it admits direct sums. Okay. Now we can shift with our compositionality diagram one further. So I'm taking the second circle in the previous diagram. I'm adding one more circle. So now I can also look at the forgetful functor that takes an additive category and simply forgets that it's additive and just looks at it as a pre-additive category. And there is, again, a right adjoint, a universal, uniquely defined right adjoint up to equivalence called the additive closure. Yeah. And the question is, what does this guy mean? What is this additive closure? So how to interpret the additive closure? Maybe on a specific example. So let R be a K-algebra. So you remember K-algebra was just a K-linear category on one point. It turns out that the additive closure of R is nothing but the category of matrices. What is the category of matrices? It has the natural numbers, including 0 as objects. So these are the dimensions of the matrix. And a matrix is a morphism between its number of rows and its number of columns. Okay. And this category is equivalent and hence an excellent computer model for the category of finitely generated free left R modules of finite rank. Okay. So now we need to say additive closure of R, and you see now the expressivity. Yeah, I want to express finitely generated free modules. I take a ring, view it as an algebroid on one object, a K-algebroid on one object, and just say additive closure, which is simply a categorical construction. It has basically nothing to do with matrices. So in this sense, it's somehow invented. And the second nice thing about this category that it's Alban's favorite category. And category theory is just telling us that it has just invented matrix calculus. So for rings, it's inventing matrix calculus. And if you replace the ring, for example, by a graded ring is not just simply a category on one object. You have to look at it as a category where the object set is the possible degrees. So you can say, take the degree group. If your degrees give you a group or an abelian monoid, you can take this as the set of objects, and then you can say a morphism from one degree to another degree are all the elements in the ring where the degree is the difference between the two given degrees. And then you can say, okay, I take the additive closure of the graded ring viewed as a category in the correct way, and you end up having homogeneous matrices. Yeah, and you see this is really very convenient for us in computer algebra. We always have the same constructions. Yeah, and category theory is perfectly guiding us. We don't need to come up with new ideas and new interfaces and new algorithm and new names for algorithms and all this. Okay, so let me maybe also show you this. So I have also something called additive closure. I've executed the first one. So let's go from the beginning again. So here I take the right quiver, the free category. I now have a field. No, actually, like in the previous slide, so I also had a field. I now take the algebroid, and now I take the pre-additive closure of the algebroid, and I see it now has 76 operations, which were installed just by 18, and here are the 18 operations, and you see now there is an addition for morphism as we had before, and now these are all the operations, and they still fit here on one thing. And you see also something called the zero object and universal morphism into direct sum and all this stuff that I just talked about. Yeah, so you see here, universal morphism from initial object, universal morphism from the zero object, universal morphism into direct sum, universal morphism from the direct sum. Where is from the direct sum? So somewhere here, it's probably before. And you see there is functoriality everywhere. So you see all this is just, you get this for free. So let's go back to this specific example that we looked at, where I simply started with the ring R and took its additive closure. And here I even get more, because this ring as a pre-additive category has more structure than the category algebra I had before. And I see here the list of primitively installed. This is already more. And I see the list of all installed, the 199, they simply don't fit anymore on this slide. So I have to make it scrollable for you to see it. But here are more things I can really compute. So I'm taking the number 2 and viewing it as an object in the category. So this is the row module of rank 2. This is the free module of rank 2. This is the module of rank 3. So the 2 is now interpreted as a free module. I now take a matrix, interpret as an morphism in the category. And now I can compose. I can look at the source, at the range, and I can look at the outcome of the composition. Here, so it's telling me from the bottom row up, you should read it from here. So this is a morphism in rows. It has the source, this guy, the target, this guy, and this is a piece of data. It's called the matrix. Yeah, good. Yeah, so now we have, through the expressivity of category theory, we have a model for the finitely generated free modules. But actually, we would like to see more. So we would like to universally add co-kernels, and even better, all finite co-limits. So the category additive closure of R, which is nothing but the category of matrices, is abelian if and only if the ring R is semi-simple. So the question is, what can we do if R is not semi-simple? So if R is a field, more or less we're done. We have actually the category of all finitely generated vector spaces. But if R is Z, or as we saw, the polynomial ring in 2 variables over a field, then this is far away from being abelian. And there is a theorem from Freid in the 70s that tells us we can rectify the situation. And it starts with an additive category and considers this so-called Yoneda embedding. So it's embedding P in the category of finitely presented functors from the opposite category in abelian. in the category of abelian groups. This has another computer-friendly model, but this is actually conceptually the nicest description of this Fried construction. A is standing for abelian because of the following. So then A of P is additive and has co-kernels. The has is missing, hence all finite co-limits. But if P has so-called weak kernels, these are the kernels, but where we don't insist on the uniqueness of the universal morphism. If it has weak kernels and decidable lifts, then A of P is abelian, and it has the decidable equality of morphisms. So once we have two morphisms, we can decide if they're equal or if a morphism is zero. So what is the connection to Grosvenor basis theory? And this is also stuff known to Alban. This weak kernels in P, in our previous example of RMAT, is nothing but the ability to compute syzygies over the ring. And the decidable lifts in P, the P from the previous slide, the category of matrices, is nothing but the submodule membership test in R. So because of Grosvenor basis theory, we have the full force of Fried theorem. Okay, so we now know that if we have a ring with a Grosvenor basis notion, then the Fried construction of the additive closure of the ring will be an abelian category. Okay, will be an abelian category, but which abelian category? So what does this category model? Any ideas? This is the category of finitely presented left R modules. So you started with the free, and you just need to do a categorical construction. The categorical construction was just intending to add co-kernels. But because you had weak kernels, because of the syzygies you have over the ring, because of the Grosvenor basis, you end up also having kernels. And even the abelian structure according to the theorem of Fried. So Fried proved this using, I don't know, non-constructive methods, and one of my former PhD students, Sebastian Pozor, did this in his postdoc time to prove this theorem constructively. So you see here again the expressivity of this, and now let's go back and go to Fried categories. So you will see again that I'm going up the tower. I'm building a tower of expressivity and modeling. So we start with R again, the category P, the Fried category. And now I'm asking how many operations. Now I see 253 operations. And this category knows much more about itself. It's now linear, symmetric, closed monoidal. It's closed monoidal. It's a abelian category with enough projectives. Yeah. And here is the list of the primitive ones. How many primitive did we have here? This is already a lot, 57. Here they are, and these are the 200 and something installed actually for free. Yeah. And now we can do more. Yeah, we can now take the free object, view it as an object in the Fried category. So now it's becoming a projective object in Fried. This is a projective object in Fried. Now we can take the morphism we had there and view it as a morphism in the Fried category. Now we can compute co-kernels, which were not there before. We just had before something called weak co-kernels. We can compose as usual, but now we can also take kernel embeddings. And I see here, this is maybe two, I have to split the worksheet so that it's, make here another one. And go back. Okay, so I'm computing the kernel embedding of the composition. And now I'm computing the precomposition of chi and alpha. I'm checking that the composition is 0. I'm computing now the homology object because I have kernels and co-kernels. And I can check that the homology object is 0. Yeah. Okay, good. Let's go back. So we want to go to coherent sheaves. This is more than just modules. So let A be an abelian category. A non-empty full subcategory C of A is called thick if it's closed under passing to sub-objects, factor objects, and extensions. And here's the definition of the Serre quotient. So you have a category, an abelian category A and a so-called thick subcategory, which is, by the way, also abelian. And you define a new category. So this is, again, a category constructor. And the nice thing is you just copy the objects. Yeah. And the set of morphisms is a bit more complicated. It's given by this co-limit. Yeah. And maybe you don't understand what this means. And let me show you on the next slide what this means. But first of all, we know that that A mod C is again abelian, and this localization functor which sends every object to itself and every morphism to its class on the right-hand side is an exact functor. So let's try to understand, first of all, what is the structure of an element in the co-limit, in this right co-limit. So this is what we have here is you see that if you want to encode a morphism from M to N, we have the freedom of passing to sub-objects of M and passing to sub-objects of N, such that M modulo M prime and N prime are in this thick subcategory C. Yeah. So this is the diagram. I can pass to the sub-object M prime such that the co-kernel is in the thick subcategory C. I can pass to so this N double prime should be called N prime. I can pass to a factor object such that the kernel is in C. And now I want to show you how the composition in the Serre quotient looks like. So this is now the data structure of two morphisms in the Serre quotient. A morphism in the Serre quotient is an equivalence class of triples, where you need a mono, an AP, and a regular morphism. Okay? And now I will compose and use everything I have in the category A to just construct one algorithm in the Serre quotient. Yeah, and you see how it runs. So first of all, you see that actually you cannot compose almost anything except that you see that this is the identity. And then you can go this way here. So this gives you a map, which we call alpha, but somehow it goes in the wrong direction. So let's see later. And now you are in the abelian category A. And in A, you have the kernels and the co-kernels. They give you images and co-images. So you can do this simply by a categorical construction. You get the image and the co-image. And on the left-hand side, you have something which is called a co-slice diagram. From this, you can take the pullback. On the right, you have a slice diagram. For this you can take the push out, and then you can forget everything in between. And you almost get, again, a data structure that you like. You see here, you have the composition of two monos. This is a mono, a composition of two APs. This is an AP, and a composition of three morphisms. But this guy is actually looking in the wrong direction. And here you need the last axiom of abelian, which tells you that this guy is invertible. And this is how the algorithm for composition in the Serre quotient looks like. And you see, actually, we needed almost every algorithm from the underlying category A. Yeah, and you see how the C is rising. Yeah, we are taking categories that are using algorithms from categories below, which have less semantic, to get up to higher semantic. This is the rising C philosophy. Yeah. So, and what we proved is that all this can be done constructively. So let's see a thick subcategory of the abelian category. If A is constructively abelian and the membership in C is decidable, then A mod C is constructively abelian and the equality of morphisms is also decidable. So let me show you what this, So first of all, some examples. So if S is the graded polynomial ring in the variable x0 to xn, then you can look at the category of graded, finitely generated graded S modules, and you can mod those out which are supported on 0. Yeah, these are the so-called finite length graded modules. And if you take this Serre quotient, then you are precisely modeling coherent sheaves on Pn. Yeah, and remember, please remember that the only thing we changed in this category is not the objects. So we can say a coherent sheaf is just a module if you change the sense of the morphisms. You see, you are modeling the basic data structure of the category are the morphisms. It's not the objects. The objects are just placeholders, as you saw on previous slides. Yeah, it's just 1 and 2 and things like this. Yeah. So this can also be done constructively in a relative way, where B is a ring where you also have Grosvenor bases. And you can also generalize this not just for projective spaces, but for smooth toric varieties. And you can even drop smooth, but then you need more. Yeah, the modeling is not as simple anymore. So let's do at least the first example on a slide. This is called CoP1. So this is now loaded. So I'm defining the field of rationals. And now the polynomial ring in 2 variables. So I'll go for P1, the projective line. So here is the graded left presentations. Again, this is a tower of category constructors. And these are 179 operations installed by 40 primitive operations. The category is an add category, so it's pre-additive. It's monoidal and it's abelian with enough projectives. So I will not list you this thing here, it's irrelevant. So now I take a graded free module with degrees 1, 1, a graded free module of degree 0. We create 2 morphisms. Create a morphism. This is the morphism phi. And this phi, so this is, we're going from a graded module of rank 2 to a graded free module of rank 2 to a graded free module of rank 1. And the image should be the ideal xy. Yeah, so I'm just making a presentation of the ideal xy, the maximal ideal. And now I can ask, is this well-defined? Is this a mono? He tells me no. Is this an AP? He tells me false. Look at the image embedding. All this is in the category of graded modules. Is this a monomorphism, this embedding? Is it an isomorphism? No, because the co-kernel is the cyclic module QXY divided by the maximal ideal. Yeah, but the maximal ideal is an irrelevant ideal for the projective space. So if we do this on coherent sheaves, then things should become better. So let's look at the co-kernel module just to see that this is the module which is presented by xy. And is it 0? To be sure, no, it's not 0. So now we pass to the coherent sheaves. First of all, the membership function is Artinian. And we call it is Artinian. And now we define the Serre subcategory given by this membership function. So the subcategory of the category of graded modules over blah by the function is Artinian. This is SGR mod up 0. And now I can take the Serre quotient. So the coherent sheaves on P1 is this. And again, this is at least an abelian category. It got some less operations installed. This has just to do with the fact that I didn't tell the constructor that my Serre subcategory is also closed under the tensor product. Otherwise, I would have got the same number of installed methods. I can compute the Scheffification functor, install it as SH. And now I can apply my exact Scheffification functor on phi and ask, is and get what I call psi, and now ask, is this morphism of sheaf a mono? No. Is it an AP? And now it is an AP. Yeah. And now I can look at the co-kernel object, and now the co-kernel object must be 0. And I can also apply, I can either take the image embedding or apply the exact sheafification functor to my previous image embedding, and now this guy turns out to be an isomorphism. Yeah, it's basically the same data structure, but interpreted in another category. And in this category, it wasn't an isomorphism, and in this category, it is an isomorphism. Okay, so let's go back. And maybe this is here my last mathematical slide. I want to express ideal quotients. So to be able to talk about the very first problem that I started with, yeah? I want to talk about solvability of parametric systems of polynomial equations, yeah? And if you're in the business, then you know that one of the main operations you would like to talk about is ideal quotient, to be able to write such algorithms. So the first thing that one would ask you, okay, could you please express me the ideal quotient categorically? Yeah. And for this, you need some exercise, but actually it's doable. So the ring R is a pre-additive monoidal category. The additive closure R plus is a symmetric closed monoidal additive category, which is equivalent to the category of matrices over R. We saw this. But now we don't take the Fried closure. We don't take the abelian closure. We somehow, in this tower, we diverge. We go in a different direction. So where do we go? Now we take the slice category over the tensor unit of this monoidal category. And this is a symmetric closed monoidal Cartesian and co-Cartesian pre-additive category. All this vocabulary means you have algorithms, right? It's not just for the fun of it. It means that you have a lot of algorithm in your data structure R plus mod 1. It models the set of finitely generated ideals with explicit generators. Yeah. So if someone asks you how to model the poset of ideals with explicit generators, you just tell him, take the ring, view it as a category, take the additive closure, and then take the slice category over the tensor unit. And there you are. Okay, and now he tells you, okay, I want to forget about the generators. I just want to view the ideals. I want to get the poset of ideals. And the question is, the answer is again simple. Just look at the poset. What is the poset? This is the quotient construction in any category. You go to the category and you identify all morphism with the same source and the same target. So you mod out by the two-sided ideal of all morphisms. And it turns out that this is a symmetric closed monoidal strictly Cartesian and co-Cartesian thin skeletal category. And this is exactly the modeling of the lattice of finitely generated ideals without explicit generators. And in this, the ideal quotient has this funny description. It is the internal home between J and I. Yeah, so here you really use that you have a Cartesian closed category. Yeah, so this is the closure under the Cartesian structure. And let me show you what we did with this. So we programmed all this stuff using exactly this language. And I don't know if this is big enough, otherwise I'll enlarge it. So I'll...
You are now
unmuted.
unmuted.
Big enough, yes.
So I'll make it bigger.
Yeah.
You are now muted.
Good. So we were trying to compute moduli spaces of matroids. Matroids are abstractions of subsets of vector spaces. Yeah. So you can axiomatize subsets of vector spaces, finite subsets. And then you ask, can I, after you have a certain abstraction, then you can ask, can I realize this abstract set of vectors really as a concrete set of vectors in some vector space? But to get the vector space, you need to have a field and a vector space, right? So in this case, the dimension of the vector space is given by the by the matroid. You're just saying I am in a three-dimensional vector space, but you don't have any clue where over which fields is your stuff representable. So it's loading the package. Usually it loads faster, but my CPUs are all at max, so I have to wait. Okay, and now loading a package called matroid generation. And now I define the so-called co-atoms of my matroid. These are all the sets that lie in subspaces. In this case, they are two-dimensional subspaces of a three-dimensional space. And then I define the matroid by its co-atoms. And I would like to see where all this is defined. So can I realize this matroid? So I want to see, to look universally. So my most general ring is Z. And I load this package, Tsarisky frames. And the equations of, or the set, or the conditions for representability is a humongous set of equations and inequations. So this is a better way to visualize it. So you see here, it's a closed set. So the vanishing locus of some ideal minus the vanishing locus of another ideal minus the vanishing locus of the ideal number 199. Yeah, so this is a really complicated quasi-affine set. Yeah, so you can look at it and see this. These are the equations and inequations. Yeah, so you see here, it's this, the vanishing locus of this, minus the vanishing locus of this polynomial, so minus this hypersurface, and so on. And here is the parametrized object. So this is the columns are the would-be vectors if this matroid is representable over any characteristic. And now what I do is I go and embed this, also using the stuff that I was showing you in more advanced. I would like to embed this in a smaller ambient space, and he computes. And instead of how many variables did I have here? I have here 12 variables over Z. And I end up having, I have to wait. He's trying to get rid of as much variables as possible. And all this code is organized categorically. Yeah. And now I just have one variable left. So I succeeded to embed my quasi-affine set without loss of information in the spec of ZA9. And if I now display it, it looks much, much nicer. Okay, but remember my exceptional sets were hypersurfaces. So I can get back to this description. So you see here, there are two generators in the vanishing locus of the ideals I need to subtract. So let's do this. And this, now I have it again. And the parameterized object now looks nicer. It's just over A9. I now can look at the characteristic set. So this is the set over which I expect, I am sure there is a representation. So this is now a subset, a constructible subset of spec Z. And if I display it, it's telling me it's the entire Z axes without the prime 2 and 5. There, I do not expect to have, there are no arrangements, so no realizations of the matroid. And I now construct the iterator of this and compute the elements of this moduli space and display it. And I see here, this is giving me a realization over GF9. So this is GF3 and a degree 2 extension. I do it again. The next element in the moduli space, I get something which is now over GF7. So you see now he jumped over 2 and 5, which is extremely in line with what we see here, because there are no matroids and there are no arrangements over 2 and 5. And then I can go on. And this is again over F11 squared. But when I approach F13, I see that this is already over GF13. I don't need a field extension. And I think it's also the same over GF17. Yeah, okay. So I would say I will stop here. And if you have more questions, I also have something about the snake lemma and spectral sequences, but we can do this if you have questions. So thank you very much.
You are now unmuted.
Okay, thank you. Thank you very much. So are there any question here? If you have a question and are on the BBB server, you can just open your mic and speak, and I will have a look to the streaming server. So I do have a rather general question. How hard, how far from the classical presentation of a category theory was all the constructible part? Was it already written in the usual presentation of category theory, or was it hard work to do? You discussed it a bit with the Freud construction, but can you?
Yeah, I can show you how some code looks like. It really looks simple. Maybe I can show you this on this slide that so here is a slide where I'm computing the snake diagram. Yeah. Mm-hmm. And this is the snake. And the precomposition here, so I start with 3 morphisms, the morphism A, the morphism B, and the morphism C. You see, these are the 3 primitive morphisms, such that the composition is 0. Yeah. So this gives you a quiver, and you have to embed this quiver. So if you want really to have a computer proof of it, otherwise this is given in a concrete abelian category. If you have this in a complete abelian category, then you see that the computation of a snake will end up just having stuff like this. So this is what we write internally. This is more or less how the code looks internally, but composed over several functions. Yeah. And now we have the ability to visualize this. So now I can tell him, please show me the snake, in the meaning I didn't write one algorithm that computes the snake, but it's just the composition of the same high-level algorithm. And it's telling me, if you want to compute this snake, take your input data, compute from this one the co-kernel object, and then take the co-kernel with given co-kernel object. Here you take the push out, here you take the kernel lift, here you take blah, here you take blah. And here you take fiber product in between a push out, and this is the precompose. So this is the complexity of the code internally. And this is just a composition of, I think, I don't know, several steps. You can see them here. So this is the composition of all these steps. You have to start with the setting of the label, and then you have to go through all this. This is the co-kernel projection, co-kernel lift, kernel embedding, kernel embedding, kernel lift, and so on. And if you concatenate all of them, you get this, meaning that every one of them is just a block inside this diagram.
Okay, and each one of them is a step in the usual proof of the snake lemma.
Yeah.
Okay.
Yeah. But the nice thing is, because of the Freud construction, we even have a model of the free abelian category. So if I run this code and it tells me there is a snake, then I have a proof of the snake lemma, because I have the existence of the snake lemma in the free instance of abelian categories.
Mm-hmm.
You see?
Okay.
So for this kind of problems, you get automatically either a proof or a counterexample, right?
Mm-hmm. You can really compute the obstruction, why this shouldn't work. Yeah, it will tell you at some moment, this object is not 0. And then you can go and find is not 0 in the free model. And then you can cook up of course, this is a proof that it will not work. And then you can think about a simple example, a concrete example with concrete A, B, and C, concrete morphisms A, B, and C, where this object is really non-zero. Yeah.
Okay.
But it's a decision algorithm. Yeah. If it doesn't work, then there is no such snake. Yeah.
Can you show a bit spectral sequences? Just to see the strength of what you have done.
I have to. Yes. So let me. So I think this is too small. I have to increase the font a bit.
That's okay. At least for me, that's okay.
No. My computer is very slow now, so I'm sorry. Um, I didn't prepare a worksheet for this. So here I have a module n over the file algebra. This is this one. And if I ask Maple, I would like to solve this system. A solution is, according to Noether and Malgrange, the home set into a space of functions. This is just a placeholder of calling Maple in the background. I don't know if Maple will start, so let's try.
So it's a PDE system.
It's a PDE system, yes. So you see here the ring is this file algebra. It's polynomial in x, y, z, and it has these differential operators in the x, dy, dz. And you see the system has non-constant operators. So this is 2x d over dz squared plus 3dx plus so and so. Yeah. And this is just a placeholder for calling Maple in the background. And now if you ask Maple for the solution, Maple will tell you, I am this here, this ansatz, but you have to do this integration. So actually it didn't solve it. Yeah. And what one can show is that there is a spectral sequence called the double dualizing spectral sequence, or the great spectral sequence, that gives you a filtration in this module. Yeah. This let me recall. So you can filter the module, so filter by purity on n, and I will then show you the purity filtration and the associated spectral sequence in a moment. So if you now go and filter the module by the purity.
So it's a kind of equidimensional decomposition.
This is an equidimensional decomposition, as on my first slide. It goes and computes, and it's competing with BBB for CPU usage. Okay, and now you see it's changed. Here I had 8 relations on 2 generators. Now I have 6 relations on 3 generators. If I display n, then you see it now has a triangular structure. Yeah, and behind the scenes he was computing a spectral sequence. So the purity filtration of n is this one. These are the graded parts, and there is I think, I don't remember how to call the spectral sequence. Yes, so just the spectral sequence of this. In the background, he was computing this thing. And he started, yes, he started with this here. This was the 0th level, this first level of the spectral sequence, and here are the 3 layers that are now stable. The spectral sequence stabilized on the 2nd level. And this is the first spectral sequence, which telling me that these 3 here converge against this single guy, which is there. Yeah. And this computation was done in the same context as in the Serre quotient category. In the Serre quotient category, we have the ability to formally invert morphism. And this diagram, which I showed you, is exactly the construction of a so-called linearized category or generalized category in which you can formally invert every morphism. Formally invert every morphism means that every diagram chase is easy. If you want to go against the stream, just invert the stream formally. Yeah, and then check at the end that the snake, as regardless how long you have it, that this snake lies in the underlying abelian category. Yeah, and this is exactly what is used here. And now we can ask the system to solve it. So hom nf, call this sol. Now it comes back much faster. So this is Maple now in the background. And actually it solved the system completely. It's Maple, yeah, but Maple could not make this simplification on its own, yeah. And now I can now jump back and say on original presentation of n. So you remember n now is on these good generators, but I can jump back. Now it's back on the 2 generators and 8. And now if I display the sol again, it got recomputed in the background. And usually the presentation crashes here. But here are the 2 general solutions. Yeah, this is the F and the G you were looking at. Yeah, and we did this with this machinery in the background. You don't see it, but all the code was organized categorically through this rising C philosophy.
So what are the next steps? Derived categories?
We already have derived categories. This is the PhD thesis of Kamel. And he's handing in his thesis this month or next month. And he should defend maybe in 2 or 3 months.
So can we think about derived category for D modules? Or is it more complicated? Is it more complicated?
Yeah, what we think of derived categories, first of all, of representations of finite quivers, and then derived categories of coherent sheaves. And this is already complicated enough. Actually, there is a slide online that you can have a look at. So if you go here and just say hom alg, even the typing is slow, project. You should end up on this page, the GitHub organization, hom alg project. And then you should go to the notebooks, the Jupyter notebooks. So these are some of them, and there you will see one where derived categories are computed.
Can you explain how we can install Kappa Omag?
Yeah,
is it difficult or not? Yeah.
To install it, you just go here to the left thing. It's called installation. So instead of clicking here on Jupyter Notebooks, you click on installation. And then you send me your report that it's working or not working.
Is it difficult or not?
I had students in my computer algebra course. And with this here, they managed to install it. So I'm optimistic. But you know, this is all depending on other components, and of course, it's always a moving target. Such a complex amount of software. So just let me go to this here, and then you have to click on tilting equivalence. This is a worksheet, a notebook where you have computations really with derived categories. And you see here more equivalence. It's not just usual equivalence of category, but it's really coming from a tilting object. Yeah, and you see the worksheet is really long. Okay. The worksheet I just showed you is this one. The Koch P1 is there. The divisional free, non-free matroid is there. Here you can find a notebook where we are internalizing the symmetric algebra, because the next project is that we want to do equivariant Grobner bases. Yeah. But this is the future project. So if we manage to do this and we manage to have equivariant Grobner bases over algebraic groups or Lie algebras, then we can do computations with big systems.
Can you explain what you mean by equivariant Grobner bases? You use the symmetries to...
Yeah, so if you start with Grobner bases on a symmetric system, Grobner bases will automatically destroy all the symmetry.
Yeah.
So how to prevent Grobner bases from destroying your symmetry? It should have no choice than working with the symmetry. And to do this, you have to put the symmetry in the data structure of the polynomials. And what we do is we internalize the very notion of a polynomial ring. We internalize it in the tensor algebra, in the tensor category of the object of the symmetry object we want to study. So if it's an algebraic group or a Lie algebra. And here we did this just for the group S4. Yeah.
So it's meaning that you have to know the symmetry of the system, and then you include them into your computation.
Yes, I have first of all to write down the action, so to write down the symmetric algebra in a symmetric way. And I have no option then to do this using category theory, because you don't only need in this case, for example, you don't even only need the abelian structure, you really need the monoidal structure of the tensor category. You need the associators and you need the braidings. And this is something that actually no computer algebra offers up to the moment. And we did that. You can, if you go through the worksheet, you will see here that you're computing the associators, you see there? And we compute the braidings. Yeah. And now we can construct the internalized symmetric algebra really in this category. And then we can multiply monomials. And you see now that the thing is not even associative anymore. You see, we can now take chi1. It's not even generated in degree 1. So you see very funny phenomenon. Yeah, and now the multiplication of two monomials is not a monomial anymore. Okay, and you cannot do this computation without having this categorical machinery. But then you have to adapt the Grosvenor basis algorithms. I'm not saying that we have an adaptation yet, but this is the starting point. You have to view the symmetric algebra in the correct context. Yeah, Fabrice? Your mic is you're muted, Fabrice.
I'm muted. For the computation itself now of the Grosvenor basis, this imposes you some kinds of particular algorithm since you are modifying the data structure. Exactly. In particular, are you able to employ, I would say, modern algorithms that are using linear algebra like F4 or F5, or no. Are you blocked to Bohrberger algorithm?
We don't have any idea yet. This is just starting. This is just starting. Yeah.
Okay, but because you have no notion. What is the notion of leading term, for example?
We have a guess, but I don't have this in any really rigorous way I can tell you about now.
Okay, so...
But we have some guesses, and I also have the following guess, that the double exponentiality of the Grosvenor basis is coming from the fact that you have multiplicities in the multiplicities of one and the same representation inside every layer, every homogeneous degree. And if you have a strong action such that in the degrees where you, in the relevant degrees until you get to the Grosvenor basis, you don't have multiplicities. I think that the algorithm will be polynomial time.
It looks equivalent to some notion of regularity that have been defined for the modern algorithm. So they are well behaved in the case of sufficiently regular ideals, and it seems to me that the notion is quite similar.
Yeah, I think so. So I'm very optimistic when the Lie algebras
yes,
are.
You can.
Yeah.
Okay. So I'm not a specialist of Grosvenor basis, but okay. So
yeah.
the K is to be able to define a kind of notion of I don't know, leading term or something like that.
Yeah.
But for the time being, could you reverse the computation of a Grosvenor basis and try to do better computation? Say, I mean, know the final result?
No, because for example, a monomial is now a subspace. It's not just a one-dimensional subspace as it used to be. Yeah. So it's really very inside the assumptions of Grosvenor basis that you're doing really something different. Yeah.
Okay.
My monomial is now really an irreducible sub-object, which is not one-dimensional.
Okay.
Yeah.
At the beginning, in your first slide, you spoke about parameters.
Yes.
Can you say a few words about parameters?
Yes. So maybe this is also a worksheet here. So there we wanted to compute the image of this map. Yeah. So the map is given just by this trace here. So all this is you can find under this link, notebooks. Yeah. And this is also part of a paper which is now accepted in Mathematics of Computations. Actually should appear within a month. And here you see a morphism. See, so the morphism goes scheme-wise upside down, but ring-wise from bottom up. Yeah, so this is a morphism of rings, which goes from the bottom ring to the top ring. Scheme theoretically, you have a map from here to there. Yeah, and what you do is you look at the graph of the map, right? And you want to project. And project means what? Project means you want to see which fibers are inhabited, right? So this is the space of parameters, this guy downstairs. I'm using the Grothendieck convention. The scheme theoretic morphisms go from bottom down. So these are the parameters, and I want to see for which parameters T0 till T0101 are the fibers inhabited of this map. Yeah, and this is this constructible image, and you see I get it here, and this is the result.
Sorry, Mohammed, I didn't see where there is a parameter in your equation.
The parameter are all the elements of the base. This here. So you see this system is parametric.
What is the name? What are the names of the parameters?
The parameters are these here. So the parameter is telling you that this is equal to T000. So you have T0 minus.
Okay.
This is somehow a solved parametric system, but in the wrong side. You want to solve it the other way around. Yeah.
Okay.
And what we have here is we don't only compute the closure, but we even compute the complete constructible image. And
this is a Chevalier theorem?
This is Chevalier's theorem, yes. And the implementation also used, we had to go further in the tower. So after we have the poset of ideals, we have to pass to the poset of radical ideals, not to be forced to compute radicals, because this is a very expensive algorithm. But there is a trick exactly like with the Serre quotient. You change your notion of morphism, and then instead of ideals, you're talking about radical ideals, yeah, with actually no effort, yeah. And then you complete by saying, I want now differences between ideals, formal differences, and then you complete that you want to say, I want again the Boolean algebra. I want to have a lattice with joins and meets. And this is again a categorical construction. And once you have this, you can work with constructible sets. And even you have a normal form. This is also described in the paper. So if you have two constructible sets, you can bring not just test if both are equal, you can bring both to a normal form and check if they are really component-wise equal. Yeah. And this is actually one of the future applications of these equivariant Grosvenor bases, because this problem is highly equivariant. And we are just looking here at n equal to 4. For n equal to 5, we managed to do the Grosvenor basis computation. It takes 6 minutes, and I can scroll here indefinitely, but it comes out. Yeah. But of course, I don't see anything, and I would like to see something. And like to see something means that I don't want this garbage of classical data structures and polynomials. This is now for me really garbage. If the problem grows, I don't see anything of this. And what I want to see is I want to see this really written down equivariantly. And probably the answers will be more or less equal for all n. Yeah, you will when you go beyond a certain level, then you will have simply another irreducible factor of some Lie algebra of growing dimension. So the Lie algebra will grow, the irreducible module will grow, but probably the irreducible module will have the same description, regardless of the number n here.
And to compute this equivariant Grosvenor basis, you will need the gap, because of course you will use a singular or maple, but without your thinking algorithm.
I'm not sure if I will be using singular, because I'm using singular just for the for its classical Grosvenor basis engine.
Yeah, so yeah, it means that you need to have everything together.
Yeah, we will probably implement this new Grosvenor base equivariant Grosvenor basis algorithm in GAP and compile it to Julia. This is the CAP compiler, which I didn't talk about. Fabrice?
I see that you are using Grosvenor cover comprehensive Grosvenor basis, which is the slowest package I can imagine.
Which one?
Comprehensive Grosvenor basis.
Yeah. This
it's
is
just awful to use this. I guess it is triple exponential. But what is the exact need with these packages?
No, it was just for comparison. It was just for comparison with our software. So all the listed here are not the ones we use, but the one we compared our running time.
I understand, but what they are computing, in fact, is a description of a parameter space into a region over which nothing happens.
Yeah, exactly.
So the behavior is constant. I might suggest you to compare with discriminant varieties.
With this?
Discriminant varieties. Because, in fact, all these packages are computing much more than required.
Exactly. We are fair enough in the paper to say this, yes.
Discriminant varieties are directly computing a variety in the parameter space such that above each open that do not meet the variety, the behavior of the system is constant. And the main difference with, for example, Grosvenor cover or with triangular chains, regular chains, and so on, it does not require to work with lexicographical ordering, which is the bottleneck of all these algorithms.
Very nice.
It works with two blocks ordering and eliminate directly. In fact, it's very simple to understand. You have your variety, you have some inequalities. You will just compute the critical points of the projection, which includes the singular one, and the intersection of the polynomial defining the constructible set, okay? And the trace of this on the parameter space gives you the partition. Say the Zariski closure of the trace of this of the parameter space gives you the partition, and it's much more efficient. It's much more efficient than computing a full decomposition like triangular sets, because it contains much more information about the lifting, for example.
Absolutely, absolutely, yes. So I'll have a look at it. If you're interested, if you're interested, you could also have a look at this here. So just a moment.
Sure.
And see if so. This is our system. It's you have to scroll a bit. So this is the
paste and copy it somewhere.
Yeah. I mean, you can copy it from the web page.
Okay.
I can also send it to you
because it's rather simple.
It's rather simple, yes. And the next one is really big, and I would be interested.
How many?
The next one is not online.
Okay.
Yeah, I can send you the data, and I will also. I have a port to Maple, so I can try to connect our software to Maple and compare.
What is very funny is that the expression of the polynomial using traces, it looks like some minimal polynomial or something. Yeah. Because I recognize there the traces are in fact Newton sums of the product of the matrices, right?
Yeah. It's coming from some very nice stuff in quantum information theory. It's structured, yeah. It's not random.
So Fabrice, I put the link of this notebook in the chat.
Yes, but we need to paste and copy it, because when we leave.
But from the link you can paste. If you want, I can paste.
Yeah, I hope you can also find it easily. So you write down Homolog project. You should find the page, and then you should go to notebooks, and somewhere it's written here. So once you're on the page, you just click here.
I guess it could be a good occasion to discuss again, in fact.
Yeah, of course.
What I do not understand in the worksheet is which variables are playing the role of parameters.
So let me go back.
The t's.
The t's.
The t's, okay.
T, yeah, these are always the one on the base. This is the Grothendieck notation that you have a relative situation. You have a morphism onto the base.
And in the system that I just pasted, each t is one of the entry. Okay, maybe.
One of which entries? So these are
in the chat. I pasted this system. I just pasted.
Exactly. Yeah, exactly.
So
every t is one of these.
The first t is the first polynomial in S, and so on.
On the other hand, I guess it would be interesting that we send you another problem we had. Where the computation for us were very, very difficult.
Yeah, we would be very interested in this.
And maybe because we were completely unable to exploit some properties because we were using Grosvenor basis, in fact.
Yeah. Yeah. So you see here, this is a Macaulay 2, a very recent one.
Yes, I know.
Polynomial map image. I mean, this is what you find easily in, but of course this depends. And the lower in the list, the unfair the comparison becomes. You know.
Yes, I'm not a fanatic of regular change, so. but I know that. To be clever, they are computing much more than what you need there. It's also the same for comprehensive Grosvenor basis. Is the worst package I know. I don't understand this object because it's a very large family of polynomial, and the unique mathematical property of this family is that when you specialize it, then you directly get a Grosvenor basis. But I asked a question to one of the guys, asking him that exactly the following. Are you sure that it is more efficient to substitute something in your very big set of sets, or directly compute the Grosvenor basis. And it was actually a very good answer. I just in that, in my opinion, the substitution in the comprehensive Grosvenor basis to catch the information, it's more complicated than it's more complicated than directly computing the Grosvenor basis.
Yes.
For the parameter value.
So actually, my co-author in this paper is Markus Lange-Hegemann, and he's very fluent in all this, and he knows a lot how to use the not the discriminants, do you call them, and even not the result.
Discriminant variety is we didn't make a lot of publicity of that. It's just a tool we are using explicitly for parametric systems.
Yeah.
With the following remark, what means solving a parametric system? I don't think it does mean to compute a triangular set or a Grosvenor basis or something like this.
Mm-hmm.
It's to compute a partition of the parameter space.
Mm-hmm.
What is such a partition? It's a partition using an algebraic variety. Okay,
Mm-hmm.
and the discriminant variety is the smallest algebraic variety that gives you a good partition, say a partition over which you can apply on each leaf of solution, you can apply the implicit theorem function.
I see.
Okay, so this means that you have an analytic cover of all any of the open in the parameter space that do not meet the discriminant variety.
Yeah.
Okay, so this make this object at least independent from the algorithm that is used for computing it. So even if the computation might be difficult, at least the great information at the end is that you cannot find any other object. This is the minimal one. So there is no other object that gives you such a partition. Any object that would give you a partition with the same property contains the discriminant variety.
Mm-hmm.
Okay, so the name discriminant is because it generalizes the discriminant. It completely generalizes the discriminant. But instead of working with one variable, you have two sets of variables. Okay, and it behaves exactly like a discriminant. And a discriminant contains all the information, and this is a minimal object you can have. And it's independent on the way you compute it.
But you're not working really inductively with this resultant philosophy, right? Because for us, resultant mean good.
It's one block. I could give I could give you the paper. I guess in the Maple documentation you have the reference.
I'll find it. Yes. Then I'm sorry, we didn't find this software.
No. It's not a problem. But so just remember, there are two different things: the discriminant variety itself and the way you compute it.
Okay.
And separate the two things, because there are many. We give a default algorithm for computing it, but in practice, we often use other strategy for computing the same object. Yeah. But maybe it could simplify the construction, knowing that this object exists and can be computed. And at least in terms of object, you cannot do better.
Very nice. Very nice.
Okay, that was a very nice discussion. Maybe it's time to end it and hopefully have another future collaborations.
Yes, please.
So thank you very much, Mohamed, for this nice talk and discussion. Thanks to everybody, and well, we will meet at some point in the future.
Thank you all very much.
At least we close the recording.